Hey everybody, in this video we are going to go over how to sketch graphs, in particular polynomial equations. When we use the word sketch, we usually are implying that there's going to be less precision or less detail than if we were to just straight up graph. So where are we missing precision when it comes to polynomials? We are not going to be finding the maximum and minimum values of these curves. And that is something that is preserved for calculus because you use derivatives where the slope is 0 to do that. So what are the things we need to know? Step 1, you want to check if the equation is already in standard form. If it is or is not, you're going to adjust what you're doing accordingly. So y equals or f of x equals, all like terms are combined, descending exponential order. So example, that one is good, it is in standard form. Example, this is bad, it's not in standard form. We got parentheses, we need to multiply, and maybe like terms to combine, it's not in order, yada yada. Step 2, if it's not in standard form, put it in standard form. Step 3, identify the leading term. Put it down for yourself somewhere. In this case, 5x squared. Circle it, whatever you gotta do to address it. Determine the end behavior of the polynomial from that leading term, and this chart, like a little Punnett square, is going to tell you what the leading term will tell you what the end behavior, which is the limits at negative infinity and positive infinity. If you have a positive leading term, okay? If you have a positive leading term, your graph will finish pointing up. No matter what, it is what it is. If you have a negative leading term, your graph will finish on the right pointing down. It is what it is. Then, if your power out front is odd, I'm not power out front, your degree, the power of your leading term is odd. Odd implies opposite, so if the right side's pointing up, the left side points down. If the right side points down, the left side points up. So if it's odd, we have opposite behavior. If the leading degree, the leading term is a degree that is even, that implies that it's the same. So if the right side's up, so is the left side. And if the right side is down, so is the left side. So we can describe your own behavior with words: down and up and up and down and down. What if it's, that's just putting the end behavior, getting that addressed. Now we need to go and get it into factored form to figure out more information. Determine if the polynomial is fully factored. If not, fully factor it. So we need to get more information. We want factored form. The 4 common factoring methods, there's more ways to factor, of course, but GCF grouping, difference of squares, or AC method with grouping. Example, this one over here is good. It's fully factored. However, this example is not good because x squared minus 9 is not factored. You could factor that to x plus 3, x minus 3, and then we take the x minus 3, put them together, and make it x minus 3 squared. Step 2, determine the sign and degree of the leading term. So do you need to put it into expanded form, standard form? No, you could figure it out. So here, what would my, marker on my hands, what would my leading term be? It would be x to the 3rd, x to the 2nd, x to the 5th, x to the 6th, 1 x to the 5th, positive, would be my leading term. You can figure it out, okay? Determine what it is, figure out your own behavior. Great. Step 3, solve for x-intercepts. How do you get x-intercepts in any graph? I don't care what the graph is. In any graph, to get your x-intercepts, you set y equal to 0. In order to set a polynomial like this equal to 0, y equal to 0, you want it factored first, and then we apply what we call the zero product property. So you set each factor, the inside of each factor, individually equal to 0, and solve. So these x values that we just solved for are your x-intercepts. Determine the local behavior of each 0. 0 is another word for x-intercepts. So how do you get the local behavior? Look at the factor where it came from. If the factor is to the first power, it will behave like a linear. It's going to slice pretty straight through your x-axis. If the factor is squared, it's going to behave like a quadratic. It's going to touch and kind of bounce off that x-axis like a parabola. So if you zoomed in, only focused on the x-intercept, you're going to think to yourself, oh, it might be a parabola. And then you zoom out and you're like, whoa, not a parabola. It's like a polynomial. And then if it's to the 3rd power, it's going to have that little squiggle behavior going on in the graph. So again, just to, because the printout I have, my printer's running low on ink, let's just enhance this. A cubic will kind of have that little, like x to the 3rd, right? In chapter whatever that was, the cubic. And this is like quadratic, linear. I did these, what is this, chapter 1, 3, and 4 of the earlier videos. So that's how it's going to behave. Now the end behavior has no a relationship with how it behaves at the zeros. The end behavior is the overall end behavior. Locally, you got to figure it out based on other details, whether it's a y-intercept, maybe you have to pick a point to plot, whatever. So label your zeros with the numerical value and its behavior. I use L, Q, and C. You know, like I'll stick a little L before I graph it, a little Q, say, or a little C, local, linear, quadratic, or cubic. Connect the local behavior as it is required to fit the end behavior, okay? Your y-intercept could come in handy as a point to be helpful, and that would be, in this case, -7. The y-intercept you get the same way you get an x-intercept, except you plug in 0 for x, so the constant at the end. There you go. But if your y-intercept and your x-intercept are the origin, it does make it a little dicey because you need another point. That point's kind of useless, you know? So let's get into, I have 2 examples for us. I'm not going to spend too long on these, okay? We're already, where are we? Just under 6 minutes. Okay. Here, leading term. It's in standard form, happy as a clam. Leading term is 1x to the 3rd. So if that's my leading term, what's my end behavior? It's positive. It finishes up on the right. There you go. And it's odd, so it starts down on the left. So for myself, a little note, down on the left, up on the right. So when I'm drawing, I make sure I line it all up there. End behavior, done. Leading term, end behavior, finish with that. Next, get it fully factored. X squared. -4, I'm using the grouping method. X squared comes out. X minus 2 is left inside. I divided that out. -4, always the sign of the leading term. Divide that out, left with x minus 2. These match. Wonderful. Pulling that out front. X minus 2 is out front. What's left inside is x squared minus 4. Not done factoring. X minus 2 still sitting there. That's a difference of 2 squares. I get x minus 2 and x plus 2. X minus 2, I have 2 of them. We want to write it like this, and x plus 2 like that. So there we go, fully factored. So could I stick a y equals in front? I guess. A little squish, sorry, forgive me. So there is my polynomial in factored form, fully factored form, expanded form, or standard form. Now let's do some zero product property. X minus 2 equals 0, so x equals 2. Q4, quadratic behavior because of that squared on the outside of the little parenthesis house. X plus 2 equals 0. X equals -2. If you don't know how to isolate x, I mean, you got to go back to some Algebra 1 video, sorry. This is invisible 1, so it's linear behavior. Let's go over to our graph, add these details. There's 2. It's going to be quadratic when it gets there, and -2. And linear when it gets there. Suggestion, big time suggestion, is when you're graphing, I would suggest you always start on the right hand side, because if you mess up your end behavior, you're more likely to mess up where the graph started. You're less likely to mess up where the graph finishes. It's usually very obvious if the graph is positive or negative. So we know it's positive, so it's definitely finishing up. So I'm going to start my graph at the right side. I'm going to get here, smooth, continuous, quadratic behavior, though. It's got to touch and go. Do not cross your x-axis anywhere except you have an x, where you have an x-intercept. You can't cross it unless you have a doorway. The x-intercepts are your doorways. Now, while we're here, I'll label my y-intercept, but it is +8, so it should be positive. So I'm going to keep going smooth, turn around gently so it doesn't look chaotic, and then linear, so that means I slice more or less straight through. So from far away, if you were zoomed in, locally looking, you're like, oh, linear equation. Oh, not linear, right? Oh, look, it's a quadratic. Oh, no, it's not quadratic. That's what we mean when we're talking about local behavior. So now, what else do we know? The y-intercept's 8, so we could be a little extra fancy. And there you go, 8. Beautiful. Best thing you ever graphed in your life. Agree? Let's do one more. That's the end of that one. Here we go. Oh, and this equation above my head, basically ax to the n could be any power, and then your powers decrease until you get down to the first power and no power, and that's what that little equation there represents. Okay, let's see. Leading term, 2x to the 5. How's that? And behavior, positive, up on the right, odd, down on the left. I didn't mean for them to both have the same end behavior. I guess this just worked out that way. All right, so there we go. Now, factoring. Please, always, always, always look for a way to get out your GCF first if you have one. So my GCF is x cubed, so I'm going to pull that out front. X cubed, what's left inside would be 2x squared plus x minus 21. X to the third. Now in here, I'm going to do AC method with grouping. AC method, that right there, a x squared plus bx plus c, right? Quadratic in standard form. I'm going to multiply a times c, so that's negative 42. What multiplies to give me negative 42? I mean 1 and 42, 2 and 21, 3 and 14, 4 no, 5 no, 6 and 7, and that's the end of my list. B equals 1, so which pair of these numbers can give me 1? Obviously 6 and 7, but I need to multiply to be negative 42, add to be positive 1. That would be a positive 7, negative 6. So in this bracket, the x cubed sits out front. In this bracket, I'm going to split my middle term. That's my middle, that's my first, that's my last. FML, I want FOIL, I want to split my middle. So 2x squared, you stay. Using the negative 6 and positive 7, I get negative 6x plus 7x minus 21. Grouping, time. Again, x cubed just stays out front, comes along for the ride. X cubed, what's the GCF out of these two? 2x. What's the GCF out of these two? Plus 7. 2x comes out front. Divide it out. What's left is x minus 3. Plus 7 comes out front. What's left inside? Divide it. X minus 3. If this matches, we are winning. We are winning. X to the third still out front. X minus 3 comes out front as well. And what's left inside is 2x plus 7. That says 2x plus 7. That 2 is like hard to read because it's blending with the arrow. Got it? Okay, yeah. From here, factored, let's get each part equal to 0. So what's setting equal to 0? Let me just clarify, there are invisible parentheses around that right there. That's like an x minus 0, like I was doing with the h. X minus 3 is 0. 2x plus 7 is 0. X equals 0, done. X equals 3. Subtract 7. Divide by 2. Negative 7 over 2, also known as negative 3.5. Now, cubic behavior, linear and linear. And let's get going with these points. I'm going to switch my marker to a different color. I'll go back to the purple because obviously I wrote all over the graph. What are you going to do about it? 0, 3, negative 3.5. And behavior was up this way and down that way. Then labeling the numbers, we have 3, we have 0, we have negative 3.5, okay. Linear, linear, cubic. Yeah, let's go. So from here, linear means I'm slicing pretty much straight through. Then I'm going to smooth turn around. I want this to be cubic. I know I'm going to come up from under and I'm going to go up. So I'm going to go here, set it up, set it up. So nice and smooth, connect, something like this. Then I know it's got to turn around and be linear again. So I'm going to go nice, gentle, make it natural. Don't be weird. Boom. Adorable. Adorable. Now, if you had to check, you can plug in another number and see if you get a positive or negative answer. Where would I plug in and what would I plug in? I would personally plug 4 in to factored form and just say if I get positive or negative results. 4 cubed, positive. 4 minus 3, positive. 2 times 4 plus 7, positive. Positive times positive times positive. It's above, so probably doing okay. And there you go. That's your graph. That's your quickie lesson on graphing a polynomial. And the concept here is super important if you take calculus in the future to do first derivative test, second derivative test, to graph rationals. A lot of the concepts here are exactly the same. Chapter 12 is going to be graphing sine, and thumbs up if you think you can recreate this, thumbs up if you can factor, thumbs down if you are grown and still can't factor. I don't know what to tell you. Get off your phones unless you're watching a math video. Questions, comments, concerns in the comment section. Bye!